Hello everyone. Um, Welcome back to new video. Today in this video we are going to learn how to do basic ANOVA and how to do the post-hoc test after performing ANOVA analysis. If you want to see whether one treatment or one genotype is whether significantly higher than others or not, if you want to compare the means, you need to do the post-hoc test. So this is the data set for today's video, and we have a different genotypes called G1, G2, G3, G4, and we have a different treatments. One is control, and is treatment 1, treatment 2, treatment 3, and we have the yield values. So four genotypes, four different treatments, including one control, and the yield parameters. This is all the whole data is arranged in index form. So one next to each other. So we are going to R Studio now. Open the R Studio, and this is my working directory, set working directory, and import data set. Sorry, from Excel, browse. This is the data set. Open, import. This is character. This is character. This should be numeric. Here is the data. Import. So this is our data set. So we just want to see is there any enough variation within between genotypes, and is there any variation between treatments. So for that we need to do analysis called ANOVA, analysis of variance. So you already know about ANOVA as given by R.F. Fisher, and this is kind of basic analysis for all the statistics to see is there enough variation between treatments or between genotypes. So we have two factors. One factor is genotype and one factor is treatment, and one is dependent variable, that's yield. So so for doing ANOVA, the code is very simple. Just go right to model. ANOVA is shortly written as AOV, yield, and there's a genotype in interaction with the treatment. So we have two factors, so genotype interaction with the treatment, and the data set is equal to data. That's all the name of the data set, data. So just run this and do the summary model. So here you got the degrees of freedom, sum of square, mean sum of square, F value, and probability values, genotype, treatment, genotype into treatment, and residuals. The degrees of freedom and sum of square, mean sum of square, F values, and this value should be very important. Anything which is less than 0.05 at 5% level of significance. There is a level of significance that's at 5%, 1%, and 0.1%. So for 5%, that's what we usually consider in agricultural and plant breeding experiments at 5% level of significance. Anything less than 0.05, the probability F value which is less than 0.05 is significant. So this is 5.07 in 10 to the power of minus 07. That's obviously less than 0.05. So it has a good variation between genotypes. There's a good variation between treatments. And for genotype into treatment interaction, there is no much variation. The value is 0.1. It should be less than 0.05. And so after calculating, so we got to know there is a variation between genotype and between treatment, and we want to compare the means, the means of the genotypes, whether genotype 1 is giving more yield than genotype 2, or genotype 3 is giving more yield than genotype 2. We want to compare between genotypes, and we also compare between treatments, whether treatment 1 is effective than control or treatment 2 is effective than control. So for that we need to do the post-hoc test. That's the main comparisons test. There are three different kind of post-hoc tests usually we use in statistics. One is Fisher's LSD. That's quite a liberal test, the most liberal. If you want to even consider the minute differences, then usually go for Fisher's LSD. and the other is Tukey test. Is the most stringent test, very stringent, very high standard Tukey's test, and another is DMRT test, Duncan multiple range test. So if you have a more comparisons, more number of comparisons, then you go for DMRT. So for Fisher test, doing Fisher test, first you need to download a package called Agricole. So I've already downloaded package Agricole. You can download by doing install.packages inverted comma Agricole. So I already have it. I'm just going to library it, Agricole is built. And first, initially, we need to see whether we need to have a mean comparison between genotypes or between treatments. So initially, we are going to do for between treatments. So we need to do the one-way ANOVA where yield and treatment is calculated for ANOVA. So this is ANOVA yield versus treatment, and data is equal to the data set. And you can also check for the model if you want. If you want, you can check for the model summary model. You can check the ANOVA. So there's a significant variation between treatments, and if you want to run for the LSD test, least significant difference. This is the Fisher's LSD test. LSD dot test is the model, and treatment. We want to compare between the treatment and console is equal to true. Just run this. So you get. So this is the treatment T1, T2, T3, and control, and this is the mean values. The control is 4, T1 is 4.7, 5, and 5.4, and this is the grouping letters. So any similar letters, suppose here it is A, here it is B, this is not similar letters, then there is a significant difference. Anything which is having a similar letters here, suppose here is, suppose by fortunately, but we don't have any insignificant differences. By suppose it is A here, and by chance it is instead of C it is a A here, then this A and this A is not significantly different. So different alphabet shows there's a significant difference. So each treatments are significantly different than another. So control is significant. The treatment 1 is significantly higher than control. Treatment 2 is significantly higher than control. Treatment 3 is significantly higher than control. And treatment 2 is significantly higher than T1. Treatment 3 is significantly higher than T2. Whichever is got the higher value, that will be the A alphabet. And according to the lower values, then there will be B, C, D. So if any of the two alphabets are equal or the same, then it's not significantly different. If it is having if the means are having different alphabets, then there is significantly different. So similarly, we can also do compare between genotypes to see whether the genotype 1 and genotype 2 and genotype 3 and genotype 4 are giving different yield among all treatments. So we just go for Fisher LSD same again, library Agricole. I've already did this. And rather, instead of doing treatment here, we're putting genotype here. So model genotype and go for LSD test. So again, see, this is the genotype 1, the mean values, genotype 1, genotype 2, genotype 3, and genotype 4. So I told you this A and AB, we have A as common in both these two means. That's why this is not significantly different. G1 is not significantly different than G2. But AB and all this G2, G4, and G3 have B as common. So these are not significantly different. Only G1 is significantly different than G4. G1 is significantly different than G3. So different alphabets then is significantly different. Any alphabets having any mean having common alphabets. See AB having alphabets of B and A, so it's not significantly different. So anything which is shared is not significantly different. So this is Fisher's LSD. So if you want to even consider the minimal difference, then we'll go for the most liberal Posthoc test called Fisher's LSD, so given by R.A. Fisher. And another test, Posthoc test, is Tukey's Posthoc test. The same thing, we need to calculate the ANOVA year for the genotype. We are estimating the Posthoc test for genotypes. The same thing, data is equal to data. And the code for Tukey's HSD, Tukey's test is TukeyHSD model. Rather than using LSD.test, we're using TukeyHSD. So ANOVA, you can also see ANOVA and Tukey's HSD. So here it doesn't give us any grouping values in Tukey's. You need to see the probability, adjusted probability values. If anything less than 0.05 is significant. So no values is less than 0.05. So in Fisher LSD, it showed a significant difference between few groups, between genotypes. Sorry, in Fisher LSD. But in Tukey's HSD, I told you it's a very stringent test, high standard test. There was no difference between any groups. This is between G1 and G2, G1 and G3, G1 and G4, G2. So no genotypes are significantly different than each other in Tukey's test. So Tukey's is a very stringent test. That's what it shows here. So if you want to show between treatments, again do the ANOVA for treatment and summary model. So each time when you execute model, so this model will be overwritten on this model. So initially I wrote this also as a model. So each time when I execute new code which is having model, so this thing will be overwritten by this code. So everything the model, every time the model changes. So it's a default parameter in the OR. If you use the same the names, then it will overwrite the same name previously used. So we are getting the updated models. And this is for summary. So there's a significant difference between treatments. And there's a Tukey's test. And Tukey. So between treatments, so treatment and control, the adjusted p-values, these are less than 0.05. So you see, suppose T1 and control is significantly different, T2 and control is significantly different, T3 is control is significantly different. Everything is significantly different at 5% level of significance. So, so suppose you want to do, because we have a 4 genotypes, you want to do for each one genotype, see whether genotype 1 is performing, how genotype 1 is performing across different treatments. So you want to see for each genotype, then you need to subset the genotype, subset the old data. So this is the simple name called temp, and we are subsetting data genotype is equal to G1. So we'll get the temp data set which is having only one G1, and whether you want to see for genotype 1, is there any significantly different between treatments. So if the genotype is constant, we want to see is there any significantly difference between treatments for the genotype 1. So yield data we change into temp, then Tukey's HSD. See again, this only for G1, for genotype 1, there is only significant difference here. T2 and control, T3 and control, and T3 and T1 and T3 and T2. Anything less than 0.05. So again, if you want to check for G2, you can just change here G1 to G2 genotype names and run it again. So it will give for the G2. So the values are different, 0.02 and 0.03. So again, you can check it for whatever genotype you want, G3 or G4. This is for each genotype between treatments. And finally, we'll coming to DMRT, Duncan multiple range test. When you're having lot of uh, means, and if you want to compare between, there's a lot of comparison, then you usually go for DMRT. DMRT is usually used in agronomic and soil science studies. And again, you need to open a package called library agricole for this. And again, you want to check DMRT for the treatment between treatments. Is there any significantly different? Perform the ANOVA one-way analysis, one-way ANOVA, yield versus treatment. And here the data should be data. And so just go for between treatments and see the DMRT. This is the Duncan test. This is the code for the Duncan test model. The treatment and console is equal to true. And just run this code. So you get for between treatments, the Duncan multiple range test is give all the treatments are significantly different than each other. See A, B, C, D. Same as you got in Fisher LSD. But you got a different, I think even Tukey's, we got everything is significantly different except this one, except these two. We got significantly different. So again in G1, if you want to, again in DMRT, if you want to see for individual genotype between treatments, then you can run the same code as we run here and just change the Tukey's HSD to Duncan.tst, and you can change the G1 to G1, G1 to G2, G3, G4, anything like that. Run it. So in this T2 and T1 is not significantly different because it's having the same alphabets, and T3 and control is significantly different. T3 and T2 is significantly different. T3 and T1 is significantly different. So again, if you want to do DMRT between genotypes, you just need to change treatment into genotypes here. Genotype, and put genotype here and run this. So you'll get the DMRT test between genotypes, and the A, B, and A is sharing A alphabet, so it's not significantly different. A, B, and B is sharing B alphabet, it's not significantly different. Only the G1 is significantly different than G3. So this is all about Posthoc test. So I'm going to paste all these codes in my comment box, and if you want to know anything more about the Posthoc test and any theoretical concepts or any more videos related to this, please comment on the comment box and I will do more videos. So thank you very much. Have a good day.